Hi, welcome. Today I'll discuss a simple example of how to compute expectation values and uncertainties. I won't be discussing the meaning behind these concepts, only a brief interpretation of the results. To make the example simple, I'll assume a quantum state given by the ket psi equals ket plus, and what will be the expectation values of our old friends Sx, Sy, and Sz, and what are the uncertainties of these operators, considering that given quantum state. For simplicity, I will start calculating the expectation value of the operator Sz, which is defined by Bra plus Sz ket plus, and we have to consider the eigenvalue equation for the operator Sz acting on the ket plus gives us plus h bar over 2 ket plus, and if you see the left hand side of this equation is the same which shows here, and then we can replace this part for the right hand side of this equation right below here. Then we have Bra plus h bar over 2 ket plus. We can take this h bar over 2 out of the brackets. Then we end up with expectation value of Sz equals plus h bar over 2. That multiply this inner product that we already know the result. It must be equal to 1. And then we get plus h bar over 2. This result should seem obvious because plus h bar over 2 is the only possible result of a measurement of the operator Sz for the state ket plus. Therefore, it must be the expectation value. I'll now calculate the expectation value of the operator Sx, following the same definition used before, Bra plus Sx ket plus. I write here the ket plus in terms of the eigenstates of the operator Sx, because if I don't do this, I cannot predict what will be the result of the Sx acting upon the ket plus. So then it is 1 over square root of 2 ket plus subscript x plus ket minus subscript x, and then we can just first take the complex conjugate of this ket plus and get the bra, and replace the bra here and the ket here, as we are used to do. And here I need to know through the eigenvalue equation what happens if this Sx act upon this ket and act upon this other ket. So we know that Sx acting upon ket plus subscript x gives us plus h bar over 2 ket plus subscript x. Therefore, if you take it in account, we will get plus h bar over 2 ket plus subscript x minus h bar over 2 ket minus subscript x. Multiplying these terms, we end up with the half plus h bar over 2 minus h bar over 2 equal to 0. Then the expectation value of Sx is 0. Again, this is what we expect, since the two possible measurements results are plus minus h bar over 2, each have 50% probability, so the average is 0, as shown by this result. I should have mentioned here for this eigenvalue equation the part of the spin down along the x direction, because I used that result in this part here when I assumed that Sx acting upon the ket minus subscript x gives minus h bar over 2. Then I'll just include this part in this equation here, basically plus minus, and plus minus. Now everything is alright. Finally, and the last expectation value is for the operator Sy. Bra plus Sy ket plus the eigenvalue equation for this operator, considering both eigenstates, are given by this expression h bar over 2 plus minus subscript y. The ket plus our given quantum state in the basis of the operator Sy is 1 over square root of 2 ket plus subscript y plus ket minus subscript y. We can just take the complex conjugate of this ket and insert here and put this ket right here and perform this calculation as I did before. And then we have multiplying these two brackets, the final answer will be plus h bar over 2 minus h bar over 2, 0. Then the expectation value of the operator Sy is 0. For the same reasons discussed before, this is what we expect. Well, to sum up, the expectation values of the operators Sz, Sx, and Sy for the quantum state ket plus in the z direction are given by plus h bar over 2, 0, and 0. I'll split this content into two parts, and the uncertainties I'll be discussing in the next video. Thanks for watching. I'll see you very soon.